Jai Hind to everyone. Today we discuss about the Laplace transformation. In last class we have discussed Fourier transformation. So there is some similarities in between Laplace and Fourier, and this is a very good method to analyze a circuit. You can see that. So first we discuss the what is Laplace transform. Basically, the Laplace transform when we are having a waveform that is in time domain. So it is basically used to represent the waveform or a signal into the frequency domain. Here, if having function ft, then we are having f transform fs, that is 0 to infinity ft e power minus st dt. This is your Fourier transform. We are having a function ft and we want to convert it into frequency domain. Basically, S is represented as sigma plus j omega. As we have discussed in Fourier series that omega is angular frequency. So that's why here we can replace sigma, it is the having very minimum value. So we can having, if it is tending to 0, then S can be j omega. In some function we can replace the S equal to j omega. So basically and also we have discussed some properties. The properties of the Laplace transform help us to find the transform pairs without directly using equations. As we derive each of these properties, we should keep in mind that definition of the Laplace transform equation, that is this one. So we are having two tables that having some properties of Laplace will be there. Here it is, table 1. If function ft, then their Laplace transform is fs. And first property, that is linearity. Okay, if we multiply the function by scalar quantity, or we add two functions, then their Laplace transform that becomes like this one. Means as it is, when we are having multiply by 2 or 3 or any quantities, then it is 2 times fs, like this one. If we are having function a1 f1t plus a2 f2t, then it having Laplace transform a1 f1s plus a2 f2s. Number second is scaling. If you are having function ft and have Laplace transform, that is fs, and we want to calculate the Laplace transform of fet, okay, then it becomes 1 upon a fs upon a. Okay, like we are having f2t, then it becomes 1 upon 2 f s upon 2. Okay, and here it is time shifting. We are shifting the time by a, positive a, means t minus a equal to 0, then t is replaced to a. When the function starts from the t equal to a, so then in that case the Laplace transform becomes e power minus as into fs. Okay, here it is frequency shifting. If e की power minus at into ft, we are having known value of Laplace transform of ft, and we want to find out the Laplace transform of e की power minus at ft. Okay, then it is fs plus a, fs plus a. Here it is time differentiation. If we are having a Laplace transform of ft, then we can find out the Laplace transform of df upon dt, that is sfs minus f0 minus. And if we are having n number of differentiation of that particular function, then we can go for this one, s की power n fs minus s to the power n minus 1 f0 minus s to the power n minus 2 f dash, that is the first derivative. First derivative. Okay, that is the first derivative of function ft, not fs. Okay, and some property also is there, right? The time integration. If you want to find out the Laplace transform of integration of ft, then it is 0 to ft dt, 0 to time t, ft dt integration, then it becomes 1 upon s into fs. Or you can write it fs upon s. Okay. If we multiply the function by t, then it becomes minus d upon ds of fs. Okay. And if we divide the function by t, then it becomes integration of fs from s to infinity. Time periodicity, if you are having a function that is a periodic function with period t, then it becomes the Laplace transform becomes whatever the function is f1s 1 divided by 1 minus e power minus st. Initial value f0 plus, that is limit s tending to 0 s fs. If you are having a function ft and we find out the initial value, that is 0 plus value, then if having Laplace transform of that particular function, then we can use this formula, that is limit s tending to infinity. Here it is 0 and here it is tending to infinity, that just opposite, s into fs. Okay. And the final value, that is opposite, limit s tending to 0 and s fs. Here it is convolution, if f1t convolution ft, convolution as we have discussed in f1t, f2t, we have discussed it in Fourier, it is convolution. So, what is the meaning of this convolution? That is 0 to t f1 tau f2 t minus tau d tau. Okay. So, if we are having two Laplace transform of two functions f1s and f2s and they are multiplied, then we can use this one to find out the inverse Laplace. Okay. So, here we have some expression, some functions. It is f del t, del t is the impulse function. So, the Laplace transform of impulse function is 1. Here it is ut, the Laplace transform of ut, that is 1 upon s. So, as we can see that Laplace transform, that is 0 to t ft e power minus st dt. What is the value of ut? Ut, that is this one. This is ut, value 1, this is t. So, from 0 to t, the value of function, that is 1. So, we can put 1 into e power minus st dt. So, here it is e power minus st divided by minus s, 0 to t. Sorry, 0 to infinity. Here it is infinity. It is infinity. So again, okay. So it is 0 to infinity. It is infinity. When we put the value e power minus infinity, that is 0, and minus of e to the power 0, that becomes 1, 1 upon minus s. This minus minus plus, and it becomes 1 upon s. So here we can see that the Laplace transform of ut, that is 1 upon s, like e power minus at. Okay. So we can also have the function value, that is e power minus at, and we will get the Laplace transform, that is 1 upon s plus a. And here it is t. If function is equal to t, then it is 1 upon s square. T to the power n, then it is n factorial divided by s to the power n plus 1. As you can see that t to the power n, that is n factorial divided by s to the power n plus 1. And here it is t to the power e to the power minus at, t into e to the power minus at, and the Laplace transform, that becomes 1 upon s plus a whole square. We all we can get all the expressions by using this formula only. you just change the value of ft with a little bit effort of integration, we will get the Laplace transform of that particular function. And here some also important functions are there, t to the power n e to the power minus at that have n factorial divided by s plus a to the power n plus 1. Here it is two important trigonometrical functions, sine omega t, that is omega upon s square plus omega square, cos omega t, that is s upon s square plus omega square, sine omega t plus theta, that becomes this expression, and here these are the trigonometrical expressions that are used in the function. Okay, so let's having some example. Obtain the Laplace transform of del t plus 2 ut minus 3 e to the power minus 2t. As we have discussed about the linearity, so it holds the linearity, it means we can have the Laplace transform of individual functions. So what is the Laplace transform of del t? As we, nearly we have seen that the Laplace transform of del t, that is 1. And what about ut? Ut that have a 1 upon s, and e to the power minus at, we have discussed that is 1 upon s plus a. So here the value of a, that is 2. So after simplification it becomes this one. And find out the Laplace transform of cos 2t plus e to the power minus 3t. Cos 2t, that is cos omega t, here the value of omega, that is 2. So the expression of Laplace transform of this particular function, that is s upon s square plus 4. And what about the e power minus at, that becomes 1 upon s plus 3. After simplification we will get the 2s square plus 3s plus 4 divided by s square plus 4 into s plus 3. Okay, what is the inverse Laplace? Inverse Laplace, that is basically what we are converting from time to frequency domain. Here we are converting from frequency to time domain. Okay, we are going in reverse direction. And to find out the inverse Laplace, we are going to do with the partial fraction. Okay, so we need to know some partial fraction methods. So these are simple pole method. In simple pole expression, we are having the poles like P1, P2, P3. These are the poles, and if we are having simple pole, there is no repeated pole, no complex pole are there, then we can have the value of Fs in this form. We are taking K1 to Kn as a constant. Okay, so to find out the value of K1, we are having a function Fs is, let it be 3s, let's example 2s plus 3. So it can a upon s plus 2 plus b upon s plus 3. To find out the value of a, that is s plus 2, denominator of that particular function, a upon s plus 2, then we use s plus 2 into Fs at the rate s plus 2 equal to 0. It means this is the value of s equal to minus 2. So when we multiply s plus 2 in that particular function, it becomes 3s upon s plus 3. After putting the value of minus 2, it becomes minus 6 minus 2 plus 3, so it becomes minus 6. So similarly, we can find out the value of b. So what is the value of b? That is s plus 3 multiplied by Fs at the rate s plus 3 equal to 0, means s equal to minus 3. These are the for repeated poles. The value of Kn, that is s to the power s plus p to the power n Fs, s to the s equal to the minus p. So this is for repeated poles. Okay, these are the expressions. Complex pole, for complex pole we are having this expression. Okay, and we can find out all over the transformation. Here, determine the inverse Laplace transform of particular function. by using properties, we have some thing in mind that if you are having constant value 1, that is, it means it is the Laplace transform of del t. We can get only by seeing that expressions using properties. And here it is 4 upon s plus 3, that is 4 e to the power minus 3t, 5s s square plus 16, that is the case of trigonometrical, and here it is upper in numerator, that is 5s, then it becomes minus 5 cos 4t at the rate when time is equal to 0 or greater than 0. Let's have an example of some partial fraction. Fs equal to s square plus 12 divided by s plus 2, s plus 3. So these are the simple poles. We can have the partial fraction a upon s, b upon s plus 2, c upon s plus 3. So we can calculate the value of a. What is the value of a? That is s into fs at the rate s equal to 0. So when you multiply, then it becomes s square plus 12 divided by s, that goes to cancel, s plus 3 at s equal to 0. So a, what is the value of a? That is, it becomes 12 plus 2 into 3. It is 6, 2. What is the value of b? So we can have s square plus 12, here s plus 3 at the rate s equal to minus 2. Here it is minus 2 square, that is 4, 4 plus 12 minus 2 into 1, was minus 16 upon 2, becomes minus 8. Okay, what is the value of c? That is s square, that is 3 square, means 3 into 9, 9 plus 12 divided by minus 3 into minus 1. It becomes plus, and 12 plus 9, that becomes 21 divided by 3, it becomes 7. So by using these expressions, we can find out the value of a, b, c, and lastly we get the value of inverse Laplace transform. Okay, then here it comes 2 upon s minus 8 upon s plus 2 plus 7 upon s plus 3, and that becomes 2 ut plus minus 8 e to the power minus 2t plus 7 e to the power minus 3t. This is for t equal or greater than 0. Okay, algebraic method, multiplying both sides equations by these are the basic things that we did in lower classes. You can also do that by using the expression like this one, algebraic method. Now we are having some applications to the electrical circuit. So we are going to use this Laplace technique to find out the current and voltage in the electrical network. Okay, so steps in applying the Laplace transform the circuit from time domain to the S domain. So first we transform the circuit into S domain, solve the circuit using nodal, mesh, source transformation, superposition, whatever we knew, or any circuit analysis technique with which we are familiar, and take the inverse transform of that solution, thus obtain the solution in the time domain. So first we convert the circuit that is in time domain into the S domain, then we find out the current or voltage in S domain, then we take the inverse transformation to find out the value of current and voltage into time domain. Okay, so first we discuss about the resistance. We are having a resistance, and here it is voltage, that is Vt. We don't know it is DC or AC, and here it is current It. Okay, so this can be done. We know that the Laplace transform, here it is Vt equal to R into IT. What is the Laplace transform? That is Vs, R that is constant, Is. Okay. And for inductor, the voltage current relationship, that is Vt equal to, this is inductor, this is voltage, Vt equal to L di by dt. So by using Laplace transform, the Laplace transform of Vt, that is Vs, and what about the derivative of that function It? That is, here L is outside, S Is minus I0 minus. So we can have them by multiplying by L, so SL Is minus Li0 minus. So this is your time domain circuit. We are converting it to S domain circuit. So you can see that if the initial condition are 0, in this case the initial condition, if initial condition are 0, if initial condition 0, then I0 minus equal to 0. Okay. If it is there, then we have to take this Li0 minus. It is a voltage source actually. So here it is, the transformation. In this case, Is, SL, Li0 minus. Okay. So we are having the inductor that is replaced by S into L, and having a voltage source in similar polarity, that is Li0 minus or 0, Li0. Okay. We can have them by using the voltage source in this form. It is a source transformation. By using source transformation, we convert the voltage source into the current source. Now, for capacitor, so if we are having a capacitor, so this is Vt, this is It. Okay. So we already knew that the It equal to C dV by dt, and also we are knowing that I equal to dq by dt, or q equal to integration of I dt. Okay. But we don't need to do that. Here it is Is, and it is C SVS minus V0, and if we multiply, then it becomes this one. Taking back in the form of voltage source, so Vs equal to 1 upon SC Is plus V0 minus upon S. So in this case, this voltage source, the C is replaced by 1 upon Cs, and L is replaced by L into S. R is replaced by, there is no replacement of resistance. So we can see that here we are having a 1 upon SC capacitor in S domain, and additional voltage source with opposite polarity with the source, it is V0 divided by S. Okay. If you change the source transformation, then it becomes this one. So this is the summary. And if we assume 0 initial condition, then I told you, if initial conditions are 0, then I0 minus equal to 0, V0 minus equal to 0. So by using initial condition as a 0, then here it is Vs equal to R Is, Vs equal to SL Is, Vs equal to 1 upon SC Is. So these are the different conditions. When we are using resistance or inductance or capacitance, then we can have them. Okay. And also we can define the impedance, that is in the form of Vs upon Is, Zs equal to Vs upon Is. Okay. And admittance in time domain, that is Ys equal to 1 upon Zs, Is upon Vs. The use of the Laplace transform in circuit analysis facilitates the use of various signal sources such as impulse, step, ramp, exponential and sinusoidal. So these are the excitations, so these are the signals that we use in the circuit analysis. Okay. So find VOT in the circuit, assume zero initial condition. That's good for us. We start with zero initial condition. Okay. So this is our primary circuit, that is in time domain. Everything is given. Here it is UT, that is unit step function. Unit step function. And we already knew the Laplace transform of unit step function, that is 1 upon s. Okay. So here it is 1 upon 3, 5, 1 Henry. So by transformation it becomes the Laplace transform of voltage source, that is UT, that is 1 upon s. Here the resistance is same. And what about the capacitance? So C is replaced by 1 upon Cs. So it becomes 1 upon 3 s. So 3 that goes to numerator. So 3 upon s, and here it is s into L. The value of L is 1. That becomes s. Okay. I1s and I2s. So by using the mesh analysis, we are having two mesh currents, that is I1s and I2s. So using the equations, the first one is 1 upon s equal to 1 plus 3 upon s I1 minus 3 upon s I2, and by using KVL in second mesh, 0 equal to minus 3 upon s I1 plus s plus 5 plus 3 I2, and it becomes I1 equal to this one. Substituting the value of equation 1 into 2, we will get the expression of I2, and here we find out the value of I2. And what is the V naught S? That is S into I2, and that becomes this one. Okay, we can have this into this expression, means we can elaborate, means s square plus 8s plus 18, s plus 4 square plus root 2 square, and it, after taking the inverse Laplace, V naught t, that becomes 3 upon root 2 e to the power minus 4t sine root 2t voltage, and the time is given, that is greater or equal to 0. Let's have some example more. Here the voltage source is given, that is 10 into e to the power minus t ut, and resistances are given 10, 10. We have to find out the V naught t across that particular capacitance, and here it is 2 del t, that is a current source. Okay. So, and assume V naught 0, that is given. Here it is, there is no initial conditions are there, V naught 0 equal to 5 volt. So as we can see that we change the, here it is the Laplace transform of this one, that becomes 10 upon s plus 1, 10, 10, here 1 upon Cs, and we are using here 0.5 ampere current source, and here it is 2 del t, the Laplace transform, that is 2 ampere. Okay, we are using here the current source in that particular responses. So after applying the nodal analysis, because lots of meshes are there, then we can go for a nodal analysis, that is good. So we can have them. Here it is the current passes through this one, this point, that is 10 upon s plus 1 minus V naught upon 10. Let the current I. What is the value of I? This voltage minus this voltage, because the voltage are same every point. So this voltage minus V naught s divided by 10 plus what is the current, that is 2 plus 0.5. Okay. So after solving the equation, multiplying through by 10, we can get the expression in this form, 10 upon s plus 1 plus 25 equals to V naught s plus 2, and here it is V naught, that becomes 25s plus 35 divided by s plus 1 s plus 2, and we used using Laplace, using a partial fraction, using partial fraction. Okay, so we calculate the value of A and B, that becomes 10 and 15 respectively. Here the voltage across that particular capacitance in time S domain, that becomes 10 upon S plus 1 plus 15 upon S plus 2, and by taking the inverse Laplace, we will get the value of voltage, that is 10 e to the power minus t plus 15 e to the power minus 2t ut, that the ut define that the function having value that is started from t equal to 0 or greater than 0. There is no existence of the function at t is less than 0, means at negative values there is no existence of that particular function. Okay, so we can have also some virtual load, RLE load, and denoting the initial condition t equal to 0. So similar R, L and E, by taking 3 at the same pace, V equal to Ri plus L di by dt plus E. Here it is Laplace transform, we can get the value of Is, and here it is. Okay, so that's all today. Okay, thank you.